share my screen here. There we go. So maybe before we dive into the use case, let's take a quick look at a refresher of reinforcement learning. So the graph that we see here. So basically, we are looking at 3 ingredients that we need for reinforcement fine-tuning, starting with a data set, can be unlabeled as opposed to supervised fine-tuning. We will have the model and the corresponding weights that we're going to be training. And then finally, the reward functions that we'll use to steer the model towards better completions. And so these 3 components kind of work in tandem during the training process. And so at each iteration, we're going to use our model, going to take the latest checkpoints, send it to our inference server, and have it generate a set number of completions. Those completions are then going to be scored by our reward functions. They're going to be ranked and then sent back to the trainer as a learning signal to the model. So now that we have that in the back of our head, let's dive into the use case that we have for the demo here. And so we're basically going to be teaching a model how to play the game of countdown. So let's take a look at the rules. So it's a simple game where, given a set of numbers and a target number, we want to find an equation that equals the given target. And so we can use the fine-tuned model that we have published on Hugging Face to kind of go ahead and solve this with an example answer, which is the equation that you see here, for example, where you use 76 twice, divided by itself to get 1, subtract it from 96 to get the target number of 95. So now that we have a basic understanding of the game, let's take a look at the first step for training this model, which is going to be defining the prompt. And so this is basically going to be a summary of the rules that I just explained. So using the numbers, the given set of numbers, create an equation that equals the given target. It's important to note that we can only use basic arithmetic operations like addition, subtraction, multiplication, and division, and that each number can only be used once. We're going to ask the model to produce kind of a chain of thought, step-by-step answer in between think tags, and the final equation in between answer tags. So with the prompt and a data set that we have published on Hugging Face as well, containing given numbers and targets, we can move on to the second step in the training process, which is to define those reward functions that we'll also talk about. So for this use case, we have 2 reward functions. One is going to check that the output is properly formatted. And so to recap, that's going to mean that the model is producing a chain of thought, a kind of step-by-step explanation of the answer in between think tags, and finally the target equation in between answer tags. And the reason that we want this is that, one, we can easily extract the answer, and that also the model has kind of an easy way to start learning. So easy because the second function that we have defined here is going to actually check if the answer contains the correct equation, or an equation that evaluates to the target number. And so this requires a couple of different steps, as you can see here. So we're going to first, again, check whether we can extract the answer. Then we're going to check if the numbers that were used are exactly the numbers that we had in the example, and they're also used exactly once. And then finally, if that's all the case, and it's also using the correct operators, then we'll go ahead and evaluate the equation to make sure it equals the given target. Only then we're going to give it a reward of 1, and in all other cases, we'll give it a 0 reward. Note how we also use different print statements, or can use different print statements as part of our reward functions. and they'll show up during the training process, which I will show in a second. So to recap, we have one reward function that checks the formatting and one reward function that checks that the output contains the correct answer. Now that we have a data set and the reward functions defined, we can go ahead and kick off training. For reference, we also kicked off a supervised fine-tuning training job, just so we can compare. But importantly, for this demo, we have the creation of a reinforcement fine-tuning job, which only needs the data set that we defined and the reward functions, the formatting and the correctness one. So with that, let's take a look at what it looks like in the Predabase platform. So I'm looking at a training job that's currently in progress. And as I mentioned, you see the logs as printed from the reward functions. They show up here. We can see for each completion what exactly is going on and potentially where it's failing. Let's say it's not using the correct numbers. The equation might be incorrect, and so on. And so this gives us a bit of an in-depth view into the training process, and this also allows to correct that without losing all your training progress. And in addition to that, you'll also be able to make training harder as the job progresses. So besides the logs, you can also dive into very specific completions. So let's say for this specific prompt, we can see how the model progresses throughout different epochs. So on the left side, we have the completion for the first epoch, which is an incorrect equation. And as you see on the second epoch, that actually improves and is able to also get the full reward with the correct formatting and the correct equation. To get a bit of a high-level understanding of the training progress, you can look at the graphs for our reward function and see how they progress over time, either in Predabase or in weights and biases through our integration. So for this specific run, you can see how on the left we have the format reward function that the model pretty quickly learns. And then once it learns that, you see how also in the middle here, the equation reward starts going up all the way to about 60% on this countdown game. And that, if we compare that to kind of the other approaches that we have used for this experiment, on the left here, you see the base model, either by directly prompting it or asking it to think step by step. And the supervised fine-tune model, which is hurting performance actually compared to the base model. And so you see for the reinforcement fine-tuned adapter, it's able to significantly outperform the other approaches for this kind of logical reasoning task. So now that we have a model trained, let's switch back to our notebook and see how we can actually use it in practice. So for that, I created a deployment for our base model, which is Qwen 2.57 billion instruct. And let's compare the different baselines on a couple of different examples. So let's start with the first example, which is the same one as in the beginning. So again, we have the numbers 96, 76, and 76 again, with a target of 95. So if we ask the base model to try and solve this, we see that it's quickly generating a number of tokens, but eventually realize that it's not able to generate a solution. And importantly, it's also not using each number only once, so it's not able to solve the task. Our supervised fine-tune adapter is doing slightly better in the sense that it's using only each number from the input only once. But again, it's not able to get to the right answer. And only the reinforcement fine-tuned model is able to get to the correct answer by dividing 76 by itself, obtaining 1, and subtracting that from 96 to get the target of 95. Finally, our second example here makes it a bit harder in the sense that we have now 4 input numbers, 92, 76, 53, and 96, with a target of 27. So let's take a look at the base model, which again quickly starts generating many tokens, but eventually ends up in a kind of a loop, and so gets stuck and is not able to generate a final answer. The supervised fine-tuned model is able to generate an answer, but not using all the input numbers. And finally, the reinforcement fine-tuned model, which is quickly trying different combinations to finally end up to a valid equation that evaluates to the target that we had. And so with that, I kind of showed how using the Predabase SDK, you can create a reinforcement fine-tuned model that is able to outperform other approaches on this kind of logical reasoning task. So I look forward to seeing what you all built. And with that, I'll hand it back over to Will.